You launch a product. It goes viral. In an instant, thousands of simultaneous users are hammering your server. The instinct is to survive the traffic spike by buying a bigger machine, more RAM, a faster processor. But the laws of physics get in the way. At thousands of requests per second, the read-write heads on a mechanical disk can't physically move fast enough to retrieve data. The CPU queues overflow. The network interface card physically cannot push any more bits through the Ethernet port. Supporting millions of users requires tearing the system apart. You have to systematically identify these physical limits and decouple the components so they can operate and expand independently. We start with the monolithic architecture. The web server, application logic, and database live inside the same machine. When traffic scales up, every request demands compute cycles. Once the CPU maxes out, requests wait in line, and the system throttles to a halt. Worse, the monolith is a single point of failure. If a memory leak in the application crashes the server, the database drops offline with it. The entire global application dies. To survive exponential growth, the application has to evolve from a single, dense object into a distributed ecosystem. The first step is isolation. We physically pull the database out of the web server and put it on its own machine. Now, the web tier and the data tier can be managed separately. This forces us to confront how we scale. Vertical scaling adds power to an existing machine. Horizontal scaling adds independent machines to a shared pool. Because vertical scaling has hardware limits, we add a load balancer to distribute requests. But this creates a hazard if the architecture is stateful. If a web server remembers a user's session data, that user is permanently locked to that specific server. If it crashes, the user drops offline. Stateful routing traps users, creates uneven traffic loads, and prevents safe scaling. The solution is a stateless web tier. All session data is extracted from the individual web servers and pushed into a shared, persistent external data store. The servers retain zero local memory. Now, an HTTP request from any user can be routed to any available web server. This enables true auto-scaling. The system programmatically spins up new servers during a traffic spike and kills them when traffic drops, without disrupting user sessions. By abstracting state away from the compute layer, the web tier gains horizontal elasticity. With the web tier scaled, a new bottleneck emerges. Asking the primary database to execute complex operations for every read request will rapidly overwhelm its physical capacity. We protect the database by introducing a cache tier. This temporary data store holds frequently accessed information in extremely fast RAM, rather than on slower disk drives. This diagram illustrates the cache-aside strategy. Before burdening the primary data service, the consumer checks the data cache. If the answer is there, it's returned instantly. The expensive database query is completely bypassed. But this introduces a synchronization problem. When data changes in the primary database, the cache must be updated so users don't receive stale information. This chart highlights the update pathways. In a dynamic cache, the application writes updates directly into the cache. In a static cache, updates go straight to the persistent data store, and the out-of-date cache value is simply deleted, forcing a fresh read later. Because RAM is expensive and finite, cache servers use eviction policies, like least recently used, to automatically delete old data and prevent memory overflows. Caching solves database operations, but it doesn't solve the speed of light. Geographic distance between the user and the server introduces network latency. For this, we use a Content Delivery Network, or CDN. This diagram maps caching across network locations. Static assets are pushed from the main application out to edge servers globally. By leveraging an application cache, an intermediate network cache, and the local browser cache, content is held as close to the user as possible. By deploying these strategies, we bypass physical disk limitations and geographic distance. Complex compute is transformed into near-instant retrieval. Caching protects the database from heavy read operations, but the primary database remains a single point of failure under heavy write loads. To build redundancy, data is replicated. A primary master database handles all data modifying commands, writes, updates, and deletes. Those changes are immediately copied to secondary slave nodes, which exclusively handle read requests. If the master node is destroyed, a slave database is immediately promoted to become the new master, ensuring the system never drops offline. Replication provides high availability, but it has a hard limit. Eventually, the sheer volume of incoming write operations will outpace the processing power of a single master node. The answer is horizontal database sharding. We take a massive dataset and mathematically partition it across multiple independent database servers. A hash function takes a partition key, like a user ID, and applies a math formula to it. The result determines exactly which shard will store and retrieve that specific row of data. The traffic is perfectly divided. But sharding traditional relational databases is notoriously complex. Running queries across different shards becomes computationally expensive, forcing architects to rethink how data is structured. This drives the adoption of polyglot persistence, the strategy of using multiple, entirely different database engines within the exact same system. A relational SQL database guarantees the strict compliance required to process financial transactions accurately. But for high-velocity, flexible data, like a social media feed, you route that traffic to a highly scalable, non-relational NoSQL database. At massive scale, forcing all information into a single structure creates failure. Optimal architecture matches the specific data model to the specific database engine. As the system expands, we hit a mathematical reality of distributed networks. Communication breakdowns between nodes are inevitable. This is defined by the CAP theorem. It states that during a network partition, a severed connection, a distributed system can only guarantee 2 out of 3 properties: consistency, availability, and partition tolerance. Because network partitions will happen, the system forces a choice. The node must either reject the request to ensure no one reads inaccurate data, preserving consistency, or it returns the data it currently holds, even if it's stale, prioritizing availability. Architects must hard-code this choice based entirely on the specific business logic of the application. With the data layer optimized, one final bottleneck remains: synchronous, compute-heavy tasks. If a web server has to wait for a heavy processing job to finish, like rendering a video, it cannot serve other users. We eliminate this wait time using a message queue, a durable in-memory buffer that enables asynchronous communication. Under the producer-consumer model, the web servers act as producers. They instantly drop the rendering job into the queue and immediately return to handling user traffic. Completely separate worker nodes then pull tasks from the queue at their own pace. The user-facing web tier is now completely decoupled from the heavy back-end processing tier. Message queues absorb the shock of massive processing demands, ensuring the application remains hyper-responsive to the user no matter what's happening behind the scenes. This architecture serves millions of users. The dense monolith is replaced by a specialized ecosystem. A single request bypasses the CDN, is routed by the load balancer, hits a stateless web node, checks the cache tier, and resolves via a sharded NoSQL database. This entire orchestration happens in milliseconds, completely invisible to the end user. There is no single perfect design here. Every architectural decision is an exercise in trade-offs between simplicity, redundancy, consistency, and cost. The core discipline of system design is proactively identifying physical limits and engineering specialized layers to bypass them. This graphic shows the result of that discipline: a highly available, globally dispersed network operating as a single unified entity. Scaling to millions requires abandoning centralization in favor of relentless decoupling and polyglot specialization. A truly scaled application functions as a living, meticulously orchestrated ecosystem built to anticipate and survive its own failure.